Okay, so I am going to go through some Fourier analysis that's useful for the course. So I'm going to talk about specifically the Fourier transform. I'm going to go through some of the properties. Okay, so first of all, we define the Fourier transform of a function f that is L1 in Rn. Now, right off the bat, we've got to be really careful, right? We're dealing with an unbounded domain, and so it's not true that the spaces are nested. Okay? So just because you're in L1 does not mean that you're going to be necessarily in L2 or in L3. Okay? And the converse isn't true either. So, okay, so we take f in L1. The Fourier transform is defined as in the following way. So here I'm going to define it without the 1 over square root 2 pi. So I'll define it in the mathematical way, but the 2 pi will come in the power instead. Okay, there are different ways to define it. This is one way to do it. Okay, so we know that the Fourier coefficients for a Fourier series rather, is bounded. So we try to make similar estimates here. So, okay, so the question is what space, so the ultimate question we want to ask is what space does f hat lie in? Now, immediately, just from the definition, we can see that it is going to at least be bounded. Okay? But we've got to be careful. It's not necessarily going to be L1. So, f hat is certainly in L infinity of Rn. And the L infinity norm, i.e. the upper bound, in our case, is going to be bounded above by the L1 norm of f. And this is easy to see, right? Because the norm of this, the absolute value of this function right here is 1. Okay. Furthermore, furthermore, not only is f hat in L infinity, but actually it is continuous on Rn. And in fact, yeah, so we've got this, and in fact, f hat is uniformly continuous. Okay, so it's continuous on Rn, and in fact, it is uniformly continuous. Now, be careful. You might look at this and say, actually, this f hat is very regular, so certainly it's at least going to be in L1, right? Wrong, not necessarily, right? Again, we're on an unbounded domain. Okay, so this right here is something that's giving us sort of local information, right? This right here is giving us kind of a more global information that is bounded. So we can summarize this, of course, by saying that f hat is an L infinity of Rn intersected with this continuous space. Okay, now the proof of this, so the proof that it's continuous, well, let's look at f hat. Okay, so we can approach it in the following way. We're actually going to look at, yes, so it's easier if we show that f hat is continuous at 0. Right, so first show f hat is continuous near 0. Okay, so when we do that, when we do that, we look at this quantity right here in the absolute value. This is bounded above by this right here, this norm, this absolute value, sorry. Okay, now naively we say, okay, clearly as k goes to 0, this is going to go to 0 because this quantity goes to 0, but obviously we've got to be careful, right? We've got to be careful because this is an integral, right? The integrand going to 0 is not good enough. So we use the dominated convergence theorem. And let me just remind you of the dominated convergence theorem. It says the following. So we've got a sequence of measurable functions on a space X. Okay? And we have got a function which dominates over them, and it's a positive function. Okay? And we require it to be integrable. Okay? Then, if we find that, that Fn converges to F almost everywhere, so this happens pointwise, and each of the elements in our sequence, so for all n, and it's dominated from above, and of course this is an almost everywhere requirement, then that implies that in fact actually f, f1, are all integrable, and you can interchange the limit and the integral sign, right? That's what we want to check for, to use the dominated convergence theorem. So this is a more general application, right? So a very basic example of this is if you've got a compact subset, so maybe an interval even, right? And if you can show that you can bound the integral from above, then that will immediately give you the result, right? You could bound above by the L infinity norm, but we can't do this here, okay? So, you might be tempted, if you don't think of using the dominated convergence theorem, you might be tempted to first of all try and say, oh, this is bounded above by this, and then I send it to 0, but that doesn't quite work, right? Because f is not necessarily in L infinity, right? It's in L1, right? F hat turns out to be in L infinity, but not f. And you might try and estimate this from above, but then you lose information then. If you just straight up try to estimate it from above, then you get stuck. However, this right here is clearly dominated by 2 times, so this is dominated above by 2 times the absolute value of f, and this is integrable. Okay, that's the crucial idea. We have to use the fact that f is L1. Okay, so this is dominated above, the integrand is dominated above by this, so we're guaranteed that the integrand doesn't blow up. Okay, in fact it's integrable still. And so by the dominated convergence theorem we can pass the limit, right? We can send k to 0 and we can interchange. And then the rest of the proof to show uniform continuity follows quite easily. Okay, so then what we talked about next is, so this idea of a convolution. So convolution, we know how to define a convolution. It's defined for 2 L1 functions, and it's defined in the following way. So you take this, so the convolution of them is just defined to be this. Now often what we convolute with is a family of functions called, which is called a family of good kernels. So for example, smooth bump functions and all of that. We'll get to that later. So, right, there's the basic properties. So the convolution itself is going to be in L1 of Rn, okay, and that if you take the Fourier transform, then it's the product of the Fourier transforms. Now, if you define the Fourier transform with a 1 over square root of 2 pi, then clearly you're going to have to multiply by a factor of 2 pi, square root of 2 pi. So you've got to be a little bit careful. And also a very interesting, so very useful result too. So if one of the functions are regular enough, so they happen to be in an LP space in general, then the entire convolution is going to be in the LP space of Rn. And furthermore, you get that the convolution, the LP norm of the convolution, is bounded above by the LP norm of the function f, in this case, times the L1 norm of g. So of course, this is not Holder's inequality directly, right? Okay, so then we get to this idea of good kernels, which is very important. So yeah, so let's quickly talk about it. So the motivation would be something like, if we imagine the fundamental solution to the heat equation, right, where you put a Dirac delta and you let it evolve in time. Okay, so that turns out to be a good kernel. So a good kernel has the following property. So it's a function from Rn, and in fact it's L1. So you've got an index which is just t greater than 0, okay, and kt for every t is L1 in Rn. Okay, now the important point is the following, right? What we do is we convolute good kernel with a function, okay? That's the whole point. And it turns out that, so it turns out that if f happens to be bounded, if the function we're convoluting with is nice enough, okay, well then the convolution actually converges to f. So in the limit, as t goes down to 0, kt acts like an identity, and you can recover the original function. And this is actually a very crucial point. So what is a good kernel? So a good kernel is a family of L1 functions where the index is strictly greater than 0, and you got the following. So you require that the integral of this over the entire space normalizes to 1. Next, you require that if you take the absolute value of the integral, so in some sense just the L1 norm. So if I look at essentially the L1 norm of this, now of course for every t this is finite, right? But however, it could potentially go off to infinity, right? And we don't want that. So we kind of need this to be in some sense uniformly bounded. So what we require is that the sup over all t greater than 0 of the L1 norm of k sub t is finite. Okay? So notice that this isn't the statement that kt must must be bounded. We're not saying that. Okay? We're just saying that if at every moment of time you look at the norm, then it's finite. Now this right here, so you might be tempted to say, hang on, isn't this meant to be 1? Well, no, this is the normalization right here. Okay, so essentially you can't have something like this happening, right? You can't have, I don't know, so you might have a function like this, right? And So if you integrate this, this would be 0, but I could add a little bit of extra positive area if you like, right? So, you know, I could take this and I can add a Gaussian to it, right? Normal distribution, standard normal. And I could imagine making the peaks, you know, grow to infinity as t goes to infinity, right? So that isn't allowed because of that. And then the third condition is that essentially as you move time backwards, the function has got to be localized to, yeah, it's got to end up being localized. So for all delta greater than 0, the limit as t goes down to 0 of the integral, this integral right here, kt of x dx, must be equal to 0. Okay, so the idea is that you take